So this is 4.2 linear programming, and you should have with you the lecture guide that goes with it. And so this first slide gives you this information here. So linear programming deals with maximizing or minimizing cost or profit. The solution depends on certain constraints expressed as a system of linear inequalities. So we practiced making those constraints and graphing those constraints. Any solution that satisfies the constraints, so that's the shaded region, is the feasible solution. The maximum or minimum value will occur on a corner of the feasible region. So that's why we picked out the corners on that last section. The function to be maximized or minimized is the objective function. So here is what we were given the last time, where we were just given the constraints. Now we're given the objective function. So we're going to graph these. So x greater than or equal to 0 is going to be that vertical line. Y greater than or equal to 0 is going to be that horizontal line. And here, if we let x equal 0 and y equal 0, we see that our intercepts are going to be at 4. So this is going to graph it. So this is graphing this x plus y less than or equal to 4. Our intercepts are at 4. There's the line. It's going to be graphed or shaded below because it says less than. And so here would be our feasible region. Now pick out the corners. The corners were at 0, 4. Let's go back and look at that. Here we see a corner at 0, 4. Here another corner at 0, 4. And at 0, 0. And now what we're going to do, I'm going to show you on the next slide, but what we're going to do here is we're going to take these corners that we found at 4, 0, 0, 4, and 0, 0, and we're going to plug them into this. And so x is, that'd be 3 times 4 plus 2 times 0, which gives us 12. 3 times 0 plus 2 times 4, which gives us 8, and then 0 plus 0 would be 0. So if we were maximizing, we would want the maximum one. So we maximize a profit of 12 when x is 4 and y is 0. And that's what the next slides are going to go through and show you. So our corners were 0, 4, 0, 0, and 4, 0. We plugged them all in. And then we see that P is maximized at 12 when x equals 4 and y equals 0. So here this is telling us that each of these is 1/2. So if we graph x is less than or equal to 2, that's going to be a vertical line at 2. Y is greater than or equal to 0 is going to be a horizontal line at 0. These are going to have intercepts. If you let x equal 0, y is going to be 1. Y equals 0, x is going to be 1. So you're going to have intercepts at 1, 1. Here, if we let x equal 0, y is going to be 1/2. If we let y equal 0, then x is going to be -1. So here, oh, okay, because these are by halves. So 0, 1 is what they're getting ready to graph. And then there's your 1, 0 and your line. And it says it's greater than, so it's going to go up. Now they're going to graph -1 and 1/2. And there's that line. And it says y is less than, so it's going to be shaded this way. And then we've got y0 right here. Oh, they did x2, so which is 1, 2, because remember it's by halves. And it's less than, so it's going on this side. And then y greater than 0 would be up, and so this is the feasible region. And do you see where the corner, oops, let's go back. Do you see where the corners are? So we find the corners to be 1, 0, 2, 0, 2 and 1/2, 1 and 1/2, and 1/3 and 2/3. So the way that you find these corners, they don't just magically appear, and when they're not exact, then you have to find the intersections like we did the last time. How I showed you, you can RREF it, or you can use substitution and elimination. So if you don't understand that part, just ask in class. So here's our corners. We plug them into our function. C equals 5 times y plus x. We get 1, 2, 9.5, and 3.67. It says to minimize, which would be 1, so the cost is minimized when x equals 1 and y equals 0. C is minimized at 1 when x equals 1 and y equals 0. So here, we need to graph these. Using intercepts is the easiest. So if we let x equals 0, y is going to be 6. If we let y equal 0, x will be 4. So there's the first one. And it's greater than, so it's going to shade up. This one, if we let x equal 0, y is 11 over 3, which is, what, 3 and 3 something. And if y is 0, x is 11. So there's that line. Y is greater than, so it again is being shaded up. X is greater than equal to 0 is this line, shaded this way. Y is greater than 0 is this line, shaded up. And so here's our feasible region. Now notice it has a corner here, a corner here, and a corner here. But the rest of it is kind of just open. And so our corners 0, 6, 11, 0, 2, 3, 0, 6, 11, 0, 2, 3. So you can see that's where we saw our corners. We plug them into our function. And this one says minimize. So we minimize at 5 when x is 2 and y is 3. A high school band trip will require renting buses and trucks to transport not less than 100 students. So it says make a table to represent the data and put your information in there. And we're going to use x equals buses, y equals trucks. So these are the constraints. If you do not understand where they come from, ask me in class. That it would just be easier just to ask me in class. And then minimize the cost. So there's our cost function. We have to graph them. Again, using the intercepts. Using intercepts. And again, these two, the last two that we've seen, cannot have maximums because we don't have a maximum corner. It can only have the minimums. So we find our corners, we plug it in, and the minimum is 1100 at 2 and 2. Again, I'm going to go through these. If you don't understand these last two, it'll be easier for me to show you in class. I guess there were 3 of them. So try them on your own. If you don't understand them, we will go over them in class.